In this video, I will be discussing how to solve a problem from our first exam. The problem that gave me the most trouble on midterm 1 was problem number 2 that dealt with the springs. The problem states, a block of mass m is connected to two springs. Each spring has a relaxed length L0. The spring on the left has a stiffness Ks and the spring on the right has a stiffness 2Ks. As shown in the diagram, the block is initially released from rest at x equals L0 over 3. The bottom surface supporting the block is frictionless. Let's begin with part A. Choose the block as the system and use the usual axis system with the positive x to the right and the positive y running vertically up. Just after you release the block, which external objects are interacting with the chosen system? If the block is our system, that means that the left spring, the right spring, the earth, and the surface are all of the objects acting on our system. For part B, we need to find the net force on the block at the instant the block is released. We must start from our fundamental principle, Newton's second law. We know that the net force is equal to the sum of all the forces acting on the block. Therefore, we should write that F net equals the force of the left spring plus the force of the right spring plus the force of gravity plus the normal force from the table. Since the object does not begin moving in a vertical direction, we can assume that the normal force and the force of gravity are equal, and therefore the vertical component of the net force is 0. The part of the net force we need to focus on is the horizontal component. We know that the sum of the forces of both springs will equal F net. I started by calculating the force of the left spring. The force of a spring is equal to negative k times the displacement of the spring. I then replaced these variables with the values given in the problem, which changed the equation to negative ks 4/3 L0 minus L0 in the positive x direction. After simplifying, I determined the force of the left spring was equal to negative 1/3 ks L0 in the plus x direction. Next, I calculated the force of the right spring using the same original equation and plugging in the appropriate values. This equation then read the right spring force equals negative 2Ks times 2/3 L0 minus L0 in the negative x direction. After simplifying, I found the force of the right spring to equal 2/3 Ks L0 in the negative x direction. I then added these two forces together to find the total net force. Because the force of the right spring is in the negative x direction, we can change the sign on the equation to show that it goes in the opposite direction when we add our forces. After adding the forces together, we find that the net force is equal to the vector negative ks L0, 0, 0. For part C, it says to determine the new velocity of the block a short time delta t after being released. We will once again start with our fundamental principle, Newton's second law of motion. Final velocity equals initial velocity plus the net force divided by mass multiplied times delta t. Since the system began from rest, the initial velocity is 0. We then plug in the net force we calculated in part B and get that the final velocity equals 0 plus negative ks L0 x hat divided by m times delta t. The final velocity of the system at this instance is the vector negative ks L0 delta t over m, 0, 0. For part D, we must use our answer that we calculated in the previous section to find the new position of the block. Use the kinematic equation, final position equals initial position plus average velocity multiplied by time. We can assume that average velocity is equal to the final velocity we calculated in part C. After plugging in the appropriate values, we find that the final position equals 1/2 L0 x hat plus negative ks L0 delta t over m x hat times delta t, which when simplified makes final position equal to the vector 1/3 L0 minus ks L0 delta t squared over m, 0, 0. In part E, we are asked to determine the new net force on the block. We know the net force is equal to the right spring force plus the left spring force. We use the same spring force equations, but this time plug in a newly calculated final position of the spring and replace the first part of this final position with the final position of each spring from the first time we calculated the net force. The spring force on the left is equal to negative 1/3 ks L0 plus ks squared times L0 times delta t squared over m. The spring force on the right is 2/3 ks L naught plus 2 ks squared times L naught times delta t squared over m. We can change the sign of the right equation since it's going in the opposite direction as the left equation. After adding these together, we can see that the new F net is equal to the vector negative ks L naught plus 3 ks squared times L naught times delta t squared over m, 0, 0.
This was my solution for problem 2. Thanks for watching.